Okay, so let's start on the next section. We have invited Mr. Hyeongu Kang from EQS KAIST. He's going to be present about pseudo-random quantum states. Let's welcome Hyeongu Kang with thunderous applause.
Thank you for the greeting. My name is Hyeongu Kang, as I told before, and today I would like to present a paper named Pseudo-Random Quantum State. It basically just provides the explanation and the proposition of the definition of the pseudo-random quantum state and shows what are their properties and what are some related facts. Due to the time constraint, I cannot cover all. Due to the time constraint, I cannot cover all the materials, so I'll just skip some topics like the quantum money scheme. So it is on the paper published on the Advances in Cryptology in 2018. So the basic question this paper is asking is that how to define and construct computational pseudo-random approximations of Haar randomness, which is true random in the quantum case, and what are their applications. So before we talk about it, I will just talk about the brief overview. I will just talk about the definition of the quantum pseudo-random state, which I will say PRS from now on, and how can we construct this PRS. And for the given example of the construction, we will verify this is the PRS, and then talk about the cryptographic no cloning theorem, and finish the presentation with the introduction to the PRUs. This is talking about the computational indistinguishability. So why do we care about the randomness in the quantum cases? So in the aspect of the perspective of the cryptology, the pseudo-random function PRF and pseudo-random permutations PRP are the basic building blocks in the cryptology. So natural question to ask about is, are they remain secure against the quantum attacks? And the paper says it seems to be a positive answer. And as it is a fundamental building block, talking about the quantum counterpart of the PRF and the PRP has some meaning in the quantum cryptology and some quantum information processing too. Also, it has something to do with the understanding the quantum chaos too. So quantum many-body systems are very random and it is hard to simulate. But however, we can simulate this randomness, then we can observe the nature and the behavior of the quantum chaos or quantum many-body natures, such as thermalization. However, although the quantum devices can generate the purely quantum states, in principle, generating those purely random quantum states requires exponentially deep circuit. So that's where we start to consider about the pseudo-random quantum state. So what is pseudo-random? The distribution D is called the pseudo-random if we cannot distinguish this from the random state efficiently. For example, if we are only allowed to draw polynomial number of samples from these distributions, then we cannot if we cannot distinguish this pseudo-random distribution D and the purely random distribution, and we can distinguish it. And if pseudo-random state is easier to produce, then it will be more efficient and meaningful to use that pseudo-random state. That's why we consider this the random cases. So this is kind of a summary for the notions. So we have true randomness for the uniform distribution in the classical case and Haar measure in the quantum case. And still randomness in classical is PRG, PRF, PRP. And for the quantum, we have PRS and PRU. The PRU stands for the still random unitary. Also, there is something called QISCA independence, and it is about the statistical indistinguishability, which is different from what we're saying now, the computational indistinguishability. But due to time constraint, I will not talk about this here. So I will going to give the definition of the pseudo-random quantum state. But before I begin, I would just like to talk about some notions that we have to recall. The first one is the negligible. The function epsilon kappa is called the negligible if for large enough kappa, this function is smaller than the kappa to minus c for all positive constant c. That means it is somewhat decreasing faster than the polynomial manner. So this is where how we define the negligible. This next one is just a swap test. Anybody will be familiar with it, but I will just mention it again because we will later use this in the proof. So for this given circuit, if we measure the first resistor, we get 0 for this probability and 1 for this probability. So we can just capture the nature of this inner product of two states. And this one is kind of technical thing to mention. It is about the symmetrics of space. So what we want to construct in here is the superposition of the states that are invariant under permutation. So if we have some state here and we apply a permutation to their indexes, it will change. And we want to propose all the states that are permutation to each other. This is just a technical thing that we will use later in the proof. And lastly, we will just take for granted that for the case of the Haar measure, its calculation will be like this. The phi is just a projection onto the symmetric subspaces. As we can see that omega sigma will project the given state into some permutation cases, and we will consider for all permutations. So this is the quantum secures the random functions and its permutations. So we talk about the pseudo-random function PRF is quantum secure pseudo-random function if the following holds. This statement is somewhat long, but the essential meaning that it is saying is the polynomial time quantum algorithm cannot distinguish the purely random function and the family of the PRFK when the K is chosen in random. So we choose K in random, then that K gives the PRFK, and measuring in such manner, we cannot distinguish this PRFK and just purely random function. Note that the kappa in here is just a secret parameter that the key space, domain, and range implicitly depends on it. Next one is the PRP, the key family of the permutations, and it is just seen for the PRF case, and we just replace this PRF to the PRP. So we cannot distinguish the family of the pseudo-random permutations, PRP, from the purely random permutations. And also, we will use the fact that QPRFs and QPRP exist if quantum secure one-wave functions exist. Note that if we have a QPRF, we can construct QPRP using various shuffling constructions. So if we can construct QPRP, that means we have some QPRF. Also, note that PRFK and PRPK are polynomial time computable. So we get the definition of this pseudo-random quantum state, PRS, here. It should satisfy the two definitions. First one is the efficient generation. It should generate generated efficiently by the polynomial time quantum algorithm, and also it should be pseudo-randomness. That means if we have a truly random state, that means it is from the Haar measure, the psi here, and we have only polynomial number of copies. We cannot distinguish the pure random state and this pseudo-random state, PRS. So if you want to distinguish these two states, we need very inefficient quantum algorithm, such as it requires kind of like exponentially many number of samples. So this is about the construction. So we suppose PRF is quantum secure. Then we propose that this kind of state for the family of the QPRF is this the random state. So we show the construction and prove that this is the random state. The preparing is quite simple. Just we consider some ancilla here, then we can achieve this state by applying the Hadamard gate for the first register and doing the Fourier transformation on the second register. And then, as we know, pure FK can be efficiently calculated. So we calculate the pure FKX from the first register and put it subtract in the second register. And if we just relabel this y minus pure FK as new y, then we get the extra phase pure FKX here. And we know that it only depends on x. So we can just pull it over to the first register. Then the second register just stays the same, and the first register will be changed to our desired state. That's how we construct this. And for the pseudo-randomness property, all we need to prove is it is this equation 11 in the case of case, and it is hard to just directly prove this, so we will just put we will just compare with this is f, and f is defined as follows. So only difference from the f and the pi k is just changing PRFKX to a pure random function fx. So we considering the definition of the PRFKX, it is since it is quantum secure, we cannot distinguish this PRFKX and just fx. So by definition, this will be negligible. We now show that this one is statistically indistinguishable from that of the hard random measure case. So we define the density matrix as follows. And here we use this metric basis. So from this case, we can calculate its entries as follows. And here, since fx is just a purely random function, if it is not a y is not a permutation of x, then it will vanish because it is just a summation of all the random functions that are not correlated. However, if y is the permutation of sigma x, as permutation of the x, then the fxi will be some fy equals to some fyj. So the exponent part will become 0, and it is just counting the number of m here. So only the diagonal part entries survives, and it gives the following. And the next part is just what we saw before. So for the hard random case, if we use this metric basis, it is perfectly diagonalized. So the trace distance between these two are given as this. So we only need to calculate this term, and the ratio between two terms is 1 for the sufficiently large kappa, only except for the case when mj factorial's product is 1. Then all the elements of x, that means that all elements of x are distinct. So we can calculate this one. And we know that the first term is between 1 and 1 minus negligible kappa for the sufficiently large kappa. And the second term can have the same logic. So we get this trace distance is negligible. So they are very close. That means just we can get this one, and by the triangular inequality, we can conclude that this one is negligible kappa. So we prove that this is a random state. And there's also some candidate construction for the PRS. The paper says about using the -1 instead of the omega n, and it also talks about the application of the PRF too. The remark here is that under plausible assumptions, our PRS constructions can be implemented using shallow quantum circuits of polylogarithmic depths, because we can efficiently implement the PRF, we can efficiently make this PRS state. So we can efficiently generate the pseudo-random state and it can be used as a random state if only polynomially many resources are allowed. So this is about the no-clearing theorem, and I think everybody knows about this one, no-clearing theorem. So we cannot copy the unknown quantum state, and so since random state is something we don't know, so we can expect that we cannot copy the random state easily, and it is true for the hard random measure case. And here we show that it is also true for the pseudo-random case. So what we are going to prove is here, this statement, and it is really quite simple. We just use a swap test here. So we prove this by contradiction. Suppose we have some cloning channel that copies m qubits to m plus 1 qubits with success probability kappa to minus c for some c. And we make a distinguisher D using soft test. So we have M copy goes in the cloning channel, so it gives M plus 1. And we do soft test with this one. And if the input is from the PRS, it will give this probability. And if input is from the hard random measure, then it will give this one. And definitely, definition of the negligible kappa allow us to distinguish these two probability. So it contradicts the definition of the PRS because we got the polynomial time distinguisher that distinguishes PRS and the hard random. And lastly, I would like to mention about the pseudorandom unitary and finish this presentation. So pseudorandom unitary is just same for just similar to pseudorandom state case. So it should be efficiently computable. So there should be some quantum algorithm that can compute this efficiently, and also there's a still randomness. So it cannot be distinguishable from the hard random unitary here. And the paper provides the candidate construction for the PRF. It is from the fact that if we apply this TK for the random K, then we will get some still random quantum state. So the paper's conjecture is that if we do this for many times, then it is somewhat similar to the phi K. So we will make repeating this will for the several times with different K, we will give some kind of still random stasis. But this is kind of conjecture. I tried to find some paper related to this, but I cannot find it. So I'll just introduce here. And the last thing to mention is the candidate construction for PRP. So it is just a if we have some PRP efficient quantum circuit that can compute the PRP of the X and the inverse of the PRP, this random permutations, then we can somehow implement this very efficiently to get X, the PRP KX from X. So the conjecture is that repeating this as K other more N several times, we will get some interesting results. But the conjecture shows this is just conjecture, and I tried to find some related works, but I could not find the related works. So this was the kind of brief introduction to the still random quantum state. I'd like to mention that there's some still ongoing works on this field, and for example, one of the papers of the Professor Hyuk-jung Kwon was I recently saw in the archive, and it was still random generator using the idea of mapping the n dimensional unitary to the two to the n dimensional unitary via isometry and some random permutation. So we can just display the information, and it is somewhat related to the simulating the quantum many-body dynamics. This is all I prepare, and thank you for the listening.
Okay, so anyone with questions?
일단 제가 뭐 많이 찾아보지는 못했는데요. 제가 기억하기로 권혁준 교수님 논문 질문 내용은 일단은 PRS 관련해가지고 실제로 얘를 만들어낸 서킷이 있냐 관련해서 얘기를 해주셨는데요. 제가 기억하기로 아까 마지막에 그 멘션했던 그 논문이 제 기억으로 PRS 관련된 이야기를 하고 있습니다. 그래갖고 서킷 구조가 어떻게 되냐면 우리가 이제 어떤 수도 랜덤을 만들어내고 싶으면은 일단 정보가 일단은 흩어지는 그런 걸 좀 얘기를 해야 되니까 n 디멘셔널한 그 유니터리를 2 to the n 디멘셔널한 그 유니터리 이렇게 좀 보내버리면서 정보를 좀 흩어버리고 이런 식으로 이런 아이소메트리를 좀 적당하게 퍼뮤테이션과 섞어서 구현하면 되는 걸로 알고 있습니다. 이게 pseudo random dynamics with 제 논문 이름 정확히 기억 안 나는데 이따 다시 말씀드리겠습니다. 그러니까 말씀하시고 싶은 내용이 뭔가 우리가 실제로 하 랜덤을 이용해서 뭔가 그좀 퀀텀 어드밴티지가 있는 서킷을 만들고 싶은데 그걸 만들 때 있어서 하 랜덤 대신에 수도 랜덤을 집어넣었어도 괜찮은 결과가 나오는 게 맞냐라고 말씀하시는 건가요, 지금? 정확히 말하면은 우리가 좀 폴리노미얼한 그런 리소스 제한이 있을 때는 이제 구분을 못하고 뭔가 이 구분하고 싶으면 좀 뭐 익스포넨셜하게 좀 많이 필요한 거 그렇다는 얘기입니다. 사실 제가 아직 찾아보고 있는 부분이라서 명확하게 답을 드리긴 어려운데 그래도 verification 하게 된다면은 그러니까 이게 완전히 안 되는 건 아니고 좀 리소스 많이 든다 이런 측면에서 말씀 조금 드려야 될 것 같고요. 제가 좀 많이 찾아보지 못한 그쪽 분야여가지고 정확하게 더 답은 못 드릴 것 같습니다. 좋은 질문 감사합니다.
Yeah, actually, we have one more questions in chat, but I believe time is like running low, so maybe we're going to answer those questions independently. So let's thank Mr. Hyungo Kang for his brilliant speech. Now, I would like to invite Jungwoo Lee from EQS to deliver his presentation. His presentation topic will be about quantum information theory implementation via Pulsar, which is a software developed by Pascal. So let's welcome the speaker.
Hello, hello everyone. My name is Jungwoo Lee from KAIST EQS. I am physics sophomore. I am sophomore in Department of Physics and Chemistry. First of all, I chose this topic QIT quantum information theory via Pulsar because we previously uh, on spring and summer semester we had quantum information theory study, and after that I thought that not only just studying this kind of theory, I think we should implement this in real on device, such as using this kind of platforms. Well, many of you have probably used some kind of IBM QISCA kits, but I wanted to challenge another platform. And recently, the Pascal has been expanding their company very thoroughly, and they have been get so the Pascal is actually the company that researches and implements the neutral atom based quantum computing. Here, the individual neutral atom trapped in optical tweezers are considered qubit. and its scalability are known as over 6,100 qubit QPUs. This is the most qubit ever caught recently, and in 2024, and in 2023, the Harvard Looking Group made 48 logical qubits, and it has great global controllability, and it can work on room temperature operations by applying lasers for atom cooling. So the Pascal is company started from the France, and they are expanding their companies all around the world. So their one of their roadmap in 2024 was to accomplish the 1,000 physical qubits, and they have done June. So for neutral atom QPUs, individual atoms are trapped in arrays of optical tweezers. So the optical tweezers are the kind of lasers. It catches the atom one by one. So first of all, pre-cool atoms via Doppler cooling, and then using the SLM the spatial light modulators to so first of all, detect field lattice positions, and then you perform the sub-register rearranging and apply computational gate sequence by AOM, acousto-optic modulators, and lastly, read results via fluorescence imaging. So the above image is one of the well-known neutral atom computing platforms. So before I move on, I want to compare to other platforms. For example, superconducting qubits, they have good connectivity, but their connectivity is confined in chip fabrication, so they're limiting flexibility. And although individual control is strong, but global operations are very complex and restricted. And trapped ions, such as Hyeongu, they have some ion chains, but as you know, they are considered of the pole trap, so it is one-dimensional. So it has high connectivity, but scale poorly. And photonic qubits, they have some challenging global operations because of the difficulty of synchronizing photons across the large systems. So compared to them, I think neutral atoms are very compatible than other platforms. So the Pulsar is the open source package for the design of pulse sequences in programmable neutral atom arrays. Because the neutral atom is not gate-based operations, as I mentioned, they get single qubit operations or the global operations by some lasers. So it's quite different. First of all, registers are you can think of them as qubits. They are the group of trapped atoms in some configurations. And channels can manipulate the state of the atoms by applying electronic transitions. So they are kind of applying lasers. And the pulses, the pi folds, 2 pi folds, the sequence of pulses makes the sequence. And this is one of the, I'll show you later. Two-level transitions. This is from the atomic physics. Here there are ground state and Rydberg state. So here resonant frequency. So the Hamiltonian is the rotation vector inner product by the Pauli vector. I think I can just skip this. And Rydberg states are this is the key factor of this neutral atom platform. So Rydberg states are manipulated by Rydberg channel. So the ground state and Rydberg state. And its characteristic, one of the characteristics is the Rydberg blockade radius. It has Rydberg blockade. So in certain radius, inner radius of the Rydberg blockade, you cannot have the two neighboring states, the two neighboring atoms cannot have simultaneously Rydberg states because the atom itself becomes large when they become in Rydberg states. So they have stronger interactions between the neighboring atoms, and the coefficients are the radius are given such that. So also, I mentioned that their radius gets bigger, so they have bigger dipole moments, so they have more electric field sensitivities. Here are analog approaches and digital approaches. So the Hamiltonian, it presents the first term presents the spin one-off system, and the second term presents the detuning energy term, and second term presents Ising coupling. So in analog approach, you can think of the quantum simulation, so many body interactions and ground states, many body interactions, and from the ground states, you can adiabatically you tune the parameters, and such as the Landau-Zener effect, like that. And through this analog approach, you can solve the combinatoric problems via some GNNs or QUBO. And digital approach, you might be familiar because that's just quantum gates, the discrete manipulations. So you have to notice that other than the G and H and R state, so the ground state and hyperfine state and Rydberg state, other than those three states, others are just vanished because of the laser manipulations. Here are the states and bases. So ground and Rydberg basis has the eigenstates of G and R, and digital basis has G and H. So if you measure in the basis of ground Rydberg basis, you will get 1 for the Rydberg state and 0 for remaining things, and for the digital basis, 1 for the hyperfine states, and others are 0. So here you should mention that actually the H state is lower than the ground state, but it has 1 value. So it means that when you sense the fluorescence of the results, even it has lower energy, it has fluorophore. You have to notice that the not hierarchy matters, just distinct and controllable manipulation matters. So here it is control Z gate. First of all, this is the result. Due to the Rydberg blockade effect, it induces the fluid phase of 2 qubit system conditionally. You should just mention that, for example, the first one, this one and this one has the started from the 1 state. So 1 means the H state. So you first apply the pi false, but as in the figure, the energy doesn't match it. So actually, that is just unaffected. Well, I'll show you behind, but see, it is unaffected, and the only affected is those 2 1. You get the transition to Rydberg state. And because if the first qubit becomes Rydberg state, the second qubit has the Rydberg blockade. So that one has the energy transition upper transition. So it couldn't have it couldn't absorb the energy. But in this case, you could absorb energy and you get -1 phase. So, well, this is just applied -1 global phase, but you should just notice that for the 1-1 state, it becomes -1-1. As you know in CZ in the other superconducting qubit gates. So this is the demo. So here, CC gate. This is the Raman local channel applied to the target qubit and control qubit, and below one is the local Rydberg channel that induced the pi falls on the target qubit, and if it became the Rydberg state, it induces the Rydberg blockade. So if the blockade happens, then the second qubit are not affected, but if it is not, then second qubit gets additional phase -1. Well, this is very interesting, by the way, because we previously knew that in the gate-based like something as QISCA, you apply Hadamard and that CNOT gate to implement the Bell state. But surprisingly, by just applying this CZ gate in neutral atom-based quantum computing, you can obtain the Bell state. So this is a pulsar framework, but due to the time, I will skip. So you can, well, I showed you previously some kind of manipulations in the Pulsar Studio, but you can actually install the Pulsar in your backend, your computer, and do some codes and do something. So here I want to say that the Rydberg blockade volume matters. So at least 5 micrometer below should have some interaction between the neighboring atoms. So this is the another H gate. Just applying the Raman local channel. So here, local channel means the applying only on the individual qubit. There is Raman local channel and Rydberg local channel. And there is one more channel, the global channel. This global Rydberg channel causes the pulse on globally on all atoms in the registry. Here I showed C control Z gates like this. Well, this Pulsar Studio is very graphical, so you can just manipulate those atom arrays just by your mouse, or you can actually code on the side of the Pulsar Studio. Well, I wanted to show you the topic was the QIT via Pulsar, so I wanted to show the entanglement distribution, which I showed via the CZ gate making the Bell state. But I wanted to show that quantum teleportation and superdense coding is possible also in the neutral atom, but due to the time I couldn't show up this exact result, but it is possible. You can still implement quantum Qt and supernet coding in this neutral atom pulsar. So, and actually this neutral Pascal says that they have very good algorithmic approach on some kind of combinatoric problems, such as the maximum independent set problem, well known. So here, just briefly, you see there, if there is two neighboring things, then that is not independent sets. But if there is no, such as the Rydberg state neighboring, then it is independent set. So you have to calculate the maximum independent set, and you can just put the registers and just apply the pulses on sequences, and you can, after the pulse sequences, you can obtain these two solutions have the highest probability among the possibilities. Even if you move away the one atom, you can still get the answer. And you can do more complex things, such this. Even, well, this I wanted to show that it can kind of simulate some geometric frustration in the antiferromagnetic. And I want to tell you that well, you guys heard about the VQA, variational quantum approximation. So in VQE, variational quantum eigensolver. So the variational quantum eigensolver's purpose is to find the ground state energy of Hamiltonian, but it approximates some, like for example, BO approximation or some basis sets like STO3G, and they're used for quantum chemistry and some optimization problems. They used on VQE, we used the Ravi-Kittev and Jordan-Wigner transformation used to encode quantum states into the gates. But on the other hand, here Pulsar shows the VQS, variational quantum simulation. So this simulates the time evolution of quantum state, not the static state, which means dynamic. So the open system simulations, and we can apply variational principle for time-dependent Schrödinger equation is possible. And some kind of amorphous materials or telecom network optimization is possible. Well, I couldn't tell you all, but there is other things like such as QAOA or quantum evolution kernel, and you can make some graph machine learning. Also, lastly, I want to say that in remaining winter, our study members are trying to make a Git book for implementing quantum information theory in neutral atom quantum computing environments. And more study, we want to try the quantum error correction applied logical qubits encoding methods using the Percival Cloud, Percival Studio, and entanglement dynamics and VQS on unstable chemical compounds and graph-like molecules like HA chain or it's like benzene, something like that. These are references. Thank you for listening.
Okay, so that was a brilliant speech. So if you have any questions, please feel free to ask. You can ask questions in Korean. For those in Zoom, you can ask questions via chats and we will respond. New questions? Okay, then let's thank the speaker, Jungwoo Lee, again, and maybe we're going to have a 10-minute break until like 4 p.m. and resume our next session again. So thank you.